This is now the problem-solving part. I'll do maybe half the questions, not so many. I'll try to be quick. Right. True or false? The set A by B, A times B, that's the Cartesian product, always has a finite number of elements. Well, how about this? Z times Z. The integers times the integers. So all possible sets will be of this form. So A and B belong to the integers. That's defined. And there's an infinite number of A's and an infinite number of B's. So not finite, right? So set A by B always has a finite number of elements, so that's false. Whenever you see in a true or false question like this, in this context, always, a red flag goes up. You get suspicious. You only have to find one counterexample, and that's wrong. Okay. Now the set Zm times Zn has Zm times Zn has Mn elements. Now that looks to be true. Now remember what Zn is in this context? Zn is just the set of 0, 1, 2, ... m minus 1. Right? It's of order, it has n elements, these. So there are n possibilities there, something similar, you have n possibilities there, so the number of possible pairs, remember this is the set, it's the Cartesian product, right? So you'll have n possibilities here, you'll have n possibilities there, so mn altogether, so the set Zm times Zn has mn elements, that's true. Okay. If the group G has m elements and the group H has n elements, then G times H has mn elements. Well, it's almost the same question. The only difference is these are sets. Well, actually, if the binary operation is plus, they're also groups. Okay, so that's true. Okay. 4. You cannot form the direct product G by H if G is infinite. No. You can have like your G might be Z, for example. You can define a direct product of your groups where G is infinite. It's defined, so that's false. Okay. Write down a definition for the set A by B by C. So you've got triple now. Well, you just extend it, right? So just look at this, and how about this? So you just say A by B by C would be defined as a triple, an ordered triple. So it would be A by B, A comma B comma C, right? Such that little a belongs to big A, little b belongs to big B, little c belongs to big C, right? That seems fairly obvious. Alright, okay, question 4. You can interpret the set R by R, so that all possible ordered pairs of two real numbers, okay, so R by R, as you can interpret this set, this Cartesian product, as all the points on an infinite sheet of paper. How would you interpret Z by Z? So these are integers. Well, well, here's the answer. I'll just throw it at you. Okay, it's all these points here at integer coordinates. This would be 1, 0. That would be 1, 1. That would be 1, 2. That would be 2, 1, and so on. Okay, so all these dots, if you like, at integer crossroads, like on a grid, an integer grid. Okay, last question, a bit more theoretical. That's pretty easy so far. Okay, prove. So that's a proof. If G and H are abelian, then the direct product is also abelian. Okay, so you've got G and H abelian, that means they're groups. Yeah. So abelian groups. So G and H are abelian groups. So prove that the direct product of G and H is also abelian. So since it's getting late in the night, I will. What's the question number? That's question 8. Question 6. Let me check this now. Question 6. Okay. Right. So you got the picture. G and H are both abelian groups, and you're asked to prove that the direct product group G times H is also abelian. Well, what do we know? Now G1 and G2, they belong to G, right? Big group G. And H1 and H2 belong to the abelian group H. Right? Now they're both abelian, therefore G1, G2 equals G2, G1, right? They're abelian. And similar logic, H1, H2 equals H2, H1, right? Because G is abelian, H is abelian. So any binary operation on any two of them, you can alternate, you can switch. Right? So G1, G2 equals G2, G1, similarly for H. Right? All right, now let's take any two elements of this, binary operate on them, and see if they also commute for any two, for any pair. If that's true, then this direct product group is also abelian. So what I'm saying is what we're going to try and do is, so G1, H1 times G2, H2. We've got to try and prove that that is equal to the reverse. Okay? If we can do that, we've shown that this direct product group is abelian. So we've got to try to show that that can be reversed, commuted. Okay. Now what is this by definition? Well, just use the usual thing. So this becomes G1, G2, H1, H2. But we can use these relations. Now, these commute because the big G is abelian. So this becomes G2, G1. This becomes H2, H1. Right? But what is this? Well, that is G2, H2, G1, H1. Right? And this is the flip of that. Right? So we've proved it. Therefore, the direct product group, G by H, is abelian if G and H are abelian. Right? So that's the end of the problem solving. Next lecture will be on functions. Quite a long lecture and very important. The very notion of function, like mapping, the whole concept of mapping. In a sense, pairing off. This element pairs off with that element, that kind of thing. Very important in pure mathematics. Mapping is a very basic notion. Mapping and functions are closely linked. So spend a lot of time on that, and I will ask you to really memorize the definitions. A lot of definitions in the next lecture. So I'll see you then. Ciao.